So let's just now talk about the zeros of an n degree polynomial in the same way we have talked about the zero of a linear polynomial, a quadratic polynomial and a cubic polynomial. Now we are discussing a polynomial having a degree as n. So let us suppose we are talking about the graph of y is equal to p of x, where px is nothing but a polynomial of a degree n will intersect the x-axis at most n points. So if we are talking about a polynomial p of x having the degree n, then whenever we will draw the graph of the polynomial p of x, then it will definitely cut the x-axis at most n points, and wherever it intersects the x-axis at most n points, those n points are definitely called as the zeros of this particular polynomial. So hence at the end what we can say that the polynomial p of x has at most n zeros. So this is a very important result, just like we did with the linear, cubic, quadratic. For the n degree polynomial, we can say that the graph of p of x will cut the x-axis at most n points, and those n points are nothing but called as the n zeros. Now let's just talk about some of the problems related with it. So let us suppose we are talking about the problem number 1. The problem number 1 says that the graph of y is equal to px is given below for some of the polynomials. Then find the number of zeros of p of x in each case. So we have to find out the graph, or we have to see that whether the graph is intersecting the x-axis or at how many points. So if it is intersecting the x-axis at 1 point, so it definitely means that there is 1 0 for it. If it will intersect the x-axis at 2 points, then the number of zeros are nothing but 2, and so goes on. So it says y is equal to p of x means a polynomial is in the variable x. Now let's just talk about the very first graph. As we can see in the very first graph, this red line is nothing but the graph of the polynomial y is equal to p of x, and definitely we can see that this particular graph is not intersecting the x-axis at any point. Hence the number of zeros over here are nothing but 0, or we can say there are no 0 for this particular polynomial. So for the answer, or the answer for the very first graph is nothing but the number of zeros are, or we can say the number of zeros are 0, or we can say that there are no zeros for this particular polynomial. So the answer is there are no zeros for this particular polynomial. Let's just talk about the second graph. In the second graph, we can see that the graph is intersecting the x-axis at only 1 point. It means that the number of zeros are nothing but 1. Now let's just talk about the third graph. In the third graph, we can see that the graph is intersecting at 1, 2 and 3 points. It means that the number of zeros for this particular polynomial is nothing but 3. Now let's just see the fourth graph. In the fourth graph we have a parabola, and it is intersecting the x-axis at 2 points. It means the number of zeros are nothing but 2. So the answer for the fourth one is nothing but 2. The number of zeros are 2. For the fifth one, we can see it is intersecting the x-axis at 1, 2, 3 and 4 at 4 points. Hence the number of zeros are nothing but 4. Now let's just talk about the sixth graph. In the sixth graph, we can see that it is intersecting the x-axis at the 3 points, 1, 2 and 3. Hence the number of zeros for this particular polynomial is nothing but 3. So this is the way you can able to find out the number of zeros that do exist for any particular polynomial p of x of any degree. So I hope the solution set of all these graphs or this particular question is all clear to you. Now let's just move on further. And we will talk about a very important concept, which is nothing but called as the relationship between the zeros and the coefficients of a polynomial. What is this relationship? Now let's just say. So first of all, we do know that the zeros of a linear polynomial, where the linear polynomial is of the type ax plus b with the condition that a cannot be is equal to 0 is nothing but minus b by a. We are already aware about this, that the zeros of a linear polynomial is definitely of the type minus of of b by a, where b is nothing but the constant term in the linear polynomial and a is nothing but the coefficient of x. So how we can relate it? We can say that minus b by a is nothing but is equal to minus of constant term divided by the coefficient of x. So this is nothing but the relationship between the zeros and the coefficients, because this is nothing but the zeros of the linear polynomial, that is minus b by a was the zeros of a linear polynomial, and we can express minus b by a in terms of the coefficients of a polynomial. So this is all about the relationship between the zeros and the coefficients of a linear polynomial. Now let us suppose we are talking about the quadratic polynomial. The quadratic polynomial. So consider any quadratic polynomial. So let us suppose we are considering px is equal to 2x square minus 8 of x plus of 6. Now let's just see the relationship between the zeros and the coefficients of the quadratic polynomial. So let us suppose first of all I am writing it in the formation of, or in the general form. Let us suppose I am comparing it with the ax square plus bx plus of c quadratic polynomial. So if we'll compare both of these quadratic polynomials, so what we can say? We can say that the value of a is nothing but 2, the value of b is nothing but 8, the value of c is nothing but 6. So we can say a, b and c is 2 minus 8 and 6. So let us suppose I am writing it over here as a by comparison. By comparison we can say, so let us suppose I am writing it over here that by comparison we can say that the value of a is nothing but 2 by comparison. The value of b is nothing but minus of 8. We have to take the sign as well. So a is 2, b is minus of 8 and c is nothing but is equal to 6. Now c is nothing but is equal to 6. So these are nothing but the coefficients of the quadratic polynomial. These are obviously called as the coefficients of the quadratic polynomial. Now let's just talk about finding out the zeros of this particular quadratic polynomial. How we can find out the zeros of the quadratic polynomial? Using the splitting the middle term method or with the help of the factor theorem. So let us suppose I'm using the splitting the middle term formula or the method in order to find out the zeros of this particular quadratic polynomial. So as we have, let us suppose I'm neglecting p of x, or let us suppose I'll write it. P of x is 2x square minus of 8 of x plus of 6. So we can write it as 2x square minus 8x plus of 6. We have to multiply a and c all together. So 6 into 2 is nothing but 12. So we have to look out for the two numbers whose multiplication is 12 and whose addition is nothing but 8. So these are 6 and 2. So we can express it as 2x square minus of 6x minus of 2 of x plus of 6. Now let's just take the elements common. So it is 2x x minus of 3 minus of 2 of x minus of 3. It means we can express the quadratic polynomial in the way 2x minus of 2 and x minus of 3. We can express it in this particular form. Now if we want to find out the zeros of this particular quadratic polynomial, so we have to substitute p of x as is equal to 0. P of x as is equal to 0. It means 2x minus of 2 into x minus of 3 is nothing but is equal to 0. If the multiplication of both of these terms are is equal to 0, so what we can say? We can say that either 2x minus of 2 is equal to 0, or we can say either x minus of 3 is equal to 0. So hence at the end 2x is equal to 2 or x is equal to 1 is the very first zero of this particular quadratic polynomial. And for the second one, what we can say, x minus 3 is equal to 0. It means x is equal to 3. It is nothing but the second zeros. It is nothing but the second zeros of this quadratic polynomial. So let us suppose I am expressing x is equal to 1 and x is equal to 3 in a very important or in a very different manner. Let us suppose, let alpha and beta are the two zeros of the quadratic polynomial 2x square minus of 8x plus of 6. Let us suppose alpha and beta are the two zeros of this particular quadratic polynomial, and I am taking and I am taking alpha as 1 and beta as 3. Let us suppose I am taking alpha as 1 and beta as 3. As we know that for this quadratic polynomial we have two zeros, 1 and 3, and I am taking 1 and 3 as alpha and beta, and I am expressing 1 as alpha and 3 as beta. So let us suppose I am taking the sum of these roots. So sum of the roots can be written as alpha plus of beta, obviously. Let us suppose I am adding both of these, so it is 1 plus of 3, which is nothing but is equal to 4. And further on we have the answer of alpha plus beta as nothing but 4. Further on we can express 4 as minus of 8 divided by 2. Let us suppose I am expressing the element 4 or the number 4 as minus of 8 divided by 2, because we do know that minus is nothing but plus again, so it is 8 by 2, and when we will divide 8 by 2, the answer is again 4. Now I am writing this minus 1 or minus of 8 by 2 in a different formation as minus of 8. We do know about minus of 8. Minus of 8 was actually nothing but the value b. Minus of 8 was actually nothing but the value b. It means that in place of minus of 8, we can express b divided by 2. 2, we do know about the value 2. 2 can be expressed as nothing but a. So it means that in place of 2, I can write a. So hence at the end, what we can say? We can say that the sum of roots alpha plus beta can be expressed into the formation of minus of b by a. Now let us suppose I am taking the product of the roots. So let us suppose I am taking the product of the roots. Product of the roots means we have to multiply alpha into beta. So alpha is 1 and beta is 3. So 1 into 3 is obviously nothing but is equal to 3. Now further again, we can express 3 into the formation of 6 by 2. And we do know that 6 is nothing but the value c. 6 is nothing but the value c. It means we can write 6 as nothing but c divided by a. So in place of a, we can write a. In place of 2, we can write a. Hence, at the end, what we have concluded that the sum of the roots of this quadratic polynomial, which was alpha and beta, can be expressed as alpha plus beta, which is equal to minus of b by a. And the product of the roots, when we have taken the product of the roots as alpha into beta, it can be expressed as nothing but c by a. It can be expressed as nothing but c by a. So at the end, what we have concluded that the sum of the roots alpha plus beta is nothing but is equal to minus of b by a, which is also can be written as minus of b. B is nothing but the coefficient. Let us suppose I am writing COEFF only. I am taking a suffix. So let us suppose I am writing it as coefficient of b was nothing but the coefficient of x. So this is coefficient of x divided by a is nothing but the coefficient of x square divided by the coefficient of x square. So it means that alpha plus beta can be expressed as in this formation, and in the same way, if we are taking the product alpha into beta, which was nothing but is equal to c by a, it can be expressed as the constant term divided by the coefficient of x square. So this is nothing but the relationship in between the zeros of a quadratic polynomial and the coefficients of the quadratic polynomial, that the zeros of a quadratic polynomial can be expressed as alpha plus beta, which is equal to minus b by a. This is the relationship in between the zeros and the coefficients of a quadratic polynomial. So I hope the relationship between the zeros and the coefficients of a linear polynomial is all clear to you, and the relationship between the quadratic polynomials, zeros and the coefficients is all clear to you. Now let's just move on further and talk about in general how we can express it. Now, in general, what we have concluded that let us suppose in general, if alpha and beta are nothing but the roots or the zeros of the quadratic polynomial ax square plus bx plus of c, where a cannot be 0, then first of all we can express the quadratic polynomial ax square plus bx plus c into the formation of the zeros as k into x minus alpha into x minus of beta, where k is nothing but any type of a constant. So this is nothing but the representation of the quadratic polynomial after using splitting the middle term method or either with the help of the factor theorem. Now let's just talk about the relationship. As we can see that the relationship or for any quadratic polynomial, we can say that the sum of zeros alpha plus beta can be expressed as minus of b by a, which is nothing but the coefficient of x divided by the coefficient of the x square. Similarly, in the same way, the product of the zeros alpha into beta can be expressed as c by a, which is nothing but constant term divided by the coefficient of x square. So this is nothing but the relationship between the zeros and the coefficients of a quadratic polynomial. So this is a really very important concept, because on this particular concept we will do very important question. Now let's just move on further and talk about some of the problems which are based on the relationship. So sums which are based on the relationship. Let's just talk about the very first question. It says find the zeros of the quadratic polynomial first and verify the relationships between the zeros and the coefficients. So let's just start the question or the answer or the solution set of this particular question. First of all, it says find the zeros of the quadratic polynomial. So let us suppose we have a polynomial. Let p of x be the polynomial, which is nothing but x square plus of 7 of x plus of 10. So let us suppose this is nothing but our quadratic polynomial. Now we have to use any method, either with the help of splitting the middle term method or using the factor theorem. We can able to find out the factors or the zeros of this quadratic polynomial, as we have to look out for the two numbers whose multiplication is 10 and whose sum is nothing but 7. So it is 5 and 2 obviously. So let us suppose we can express it as px as x square plus of 5 plus of 2 of x plus of 10. Now let's just solve it. Px is x square plus of 5x plus of 2x plus of 10. We can take the elements common out of these two brackets as p of x is equal to x plus 5 plus 2x plus of 5. Now further we can express it as x plus 5 and x plus 2. Now in order to find the zeros, to find the zeros, let p of x is nothing but is equal to 0. So if px is equal to 0, it means x plus 5 into x plus 2 is equal to 0. Whenever the product of any two terms is equal to 0, so what we can say, either x plus 5 is equal to 0 or either x plus 2 is equal to 0. Now let's just find out the values of the x. So we are transposing plus 5 towards the right hand side. So the value of x is nothing but is equal to minus of 5 for the very first case, and for the second one x is nothing but is equal to minus of 2. So these are the two zeros. These are the two zeros of the quadratic polynomial p of x. So let us suppose we are expressing x is equal to minus 5 and x is equal to minus of 2 as alpha and beta. So let alpha and beta are the two zeros of px is equal to x square plus of 7 of x plus of 10. So let us suppose I am taking alpha as minus of 5 and beta as minus of 2. You can take any zeros as alpha and beta. So I am expressing minus of 5 as alpha and minus of 2 as beta. Now it says verify the relationship. Now let's just verify the relationship. First of all, let's just write down the relationship. We do know that the sum of the roots which is equal to alpha plus beta is nothing but is equal to minus of b by a. So we have to verify whether LHS is nothing but is equal to the RHS or not. And further, the product of the roots is equal to alpha into beta, which is equal to C by A. Again, we have to verify that whether LHS is nothing but is equal to RHS or not. So let's just verify this particular condition. Let us suppose I'm calling it as star. Let's just start with the sum of the roots first. Let's just start with sum of the roots. So sum of the roots was of the form alpha plus beta. What is alpha? Alpha is minus of 5 plus of beta. Beta is nothing but minus of 2. Now let's just solve it. So it is nothing but minus of 5 minus of 2, which is nothing but is equal to minus of 7. 5 minus 5 minus 2 is minus 7. Now alpha plus beta is coming out to be minus of 7. Now let's just check for minus b by a. Minus of b by a, minus of b. What is the value of b? So let us suppose I am expressing p of x. Let us suppose I am expressing this p of x as nothing but ax square plus of b of x plus of c. So by comparison, what we can say? We can say the value of a is nothing but 1, the value of b is nothing but 7, the value of c is nothing but 10. So use a as 1, b as 7, c as 10. So we can write this minus of 7 as minus of b. B is nothing but 7. B is nothing but 7 divided by A. What is the value of A? A is nothing but 1. So this is nothing but minus of B by A. So hence what we are getting at the end? We are definitely getting that alpha plus of beta formation. Alpha plus of beta formation is at the end is equal to minus of B by A. So hence verified that LHS is definitely is equal to the RHS. Now let's just talk about the product of the roots. Let's just talk about the product of the roots is equal to alpha into beta. Alpha into beta. What is alpha? Alpha is minus of 5. Beta is nothing but minus of 2. This is nothing but minus minus plus, and 5 into 2 is 10. Further, we have to express it into the formation of C by A. What is C? C is nothing but 10 divided by A. What is A? A is nothing but 1. So it is 1. So hence it can be expressible into the formation of C by A. Again, LHS value is equal to the RHS value, and at the end what we can say that alpha into beta is actually is equal to C by A. So hence again LHS is equal to the RHS. So the relation is again verified that the sum of the roots is equal to alpha plus beta, which can be expressed as minus of B by A, and further the product of the roots alpha into beta can be expressed as C by A. So hence what we can say at the end, hence the result or the relationship is verified. Hence the relationship is verified that what we are getting at the end, that the alpha plus beta is nothing but is equal to minus of B by A, and product of the roots alpha into beta is nothing but is equal to C by A. So this is all about the sum, which is based on the relationship of the coefficients and the zeros of a quadratic polynomial.